part of the class. So we're talking about bonding, and this is just like a quick overview. If you're taking notes, we're going to talk about these 3 types of bonds. So you just kind of like write each one down and we'll be able to fill in a couple key points. And if you have questions, jump in with them. I do get kind of rambling when I talk about the big picture overviews. But we have got 3 types of bonds. They are metallic, covalent, and ionic. You may have heard these words before. It kind of depends on who your freshman science teacher was back in the day. Can we remember back that far? Maybe, maybe not. But they are, the names do kind of give a clue about what is what. And are these familiar concepts to you, or is this brand new? I make this awkward if you guys don't say anything and just keep waiting. Oh, something's in the chat. We got familiar. Okay. If you're unfamiliar, you want to tell me to pump the brakes. Remember that so that we can get it together. Now, there will be some gray areas in this. A lot of things are like definitely metallic bonding or definitely covalent, but sometimes we get some bonds that are a little bit of both. So there is some gray area involved in it, and we'll talk about like very obvious examples of one or the other. But if you start doing some research on your own for an upcoming research project, you'll find that there is some debate about things. So don't let it get confusing to you. If you ever need help, you can just pop in and ask, and we'll make it work. So metallic bonding is the one that you guys are less familiar with, I would guess. And metallic bonding is made of metals. Surprise. You guys got anything metallic nearby? It's in your ears right now. Yeah. Isn't that fun? Yeah, I mean, if we have wires, they're made of metal. If you got jewelry, that's made of metal. I'm gonna kind of draw my fake metallic bonds with terrible icons here. So these are gonna be my metal nucleuses that I'm putting up on the upper left. And they'll kind of line up a little bit. And then you'll get a second row where it's kind of fitting in the spaces in between, just like that. And we'll get a more different third row here. Now, metals, the ones in the middle of the periodic table, like where does that long middle place start? What row of the periodic table is it? Now we got to think a little bit. You guys got that periodic table handy? Oh, somebody put it in the chat. Yeah, it's like, it's down there. So they've got 4 shells, 4 of those levels of electrons already full. So the nucleuses of the metals are kind of far away, and they're surrounded by all of these electrons that are kind of like, the outer electrons get to bounce around, and they're shared with all of the different guys, and we call it like a sea of electrons. And one of the key things about metals that we're all taking advantage of right now is that they conduct electricity, because those outer electrons aren't held on too much. So you can get like one electron will bump into the next one down the line, and because they push each other, they'll keep bumping and they'll all move in one direction. So you can use especially copper metal to conduct electricity. That sea of electron feeling, because they're kind of bonded, but it's not like they're hanging on super tight and they're brittle. It leads to something that we call malleability. If I say malleability, does that ring a bell to you guys? Like, is that a word you've heard before? And don't feel bad if it's not. No. So that means that you can kind of squish something and bend it. Yeah. And my favorite malleable metal, I mean, all metals, if you go to the Renaissance Festival, as soon as we're allowed to do that and see the dude hitting metal stuff with a hammer to make the metal stuff into different shapes. Blacksmith. Yeah. Like, that doesn't work with wood, does it? What happens if I hit wood with a big ol' hammer? Yeah, you get broken wood. That's no fun. But metals, you can move and you can shape. Now, how do you guys feel about, this is my favorite malleable metal, gold? Yes, $. Oh, I should have been saving the chat for the people who are watching this. I have Shmoni. I like gold. It's pretty expensive. Yeah. Now, gold being expensive is this weird concept, and that's not all metals. That's just gold, but it is expensive. And if you have gold jewelry and it is what we call 24 karat gold, that is pretty pure. And if you like bite it, you'll leave teeth marks in it, which is, you know, neat, but not desirable in your fancy jewelry. So a lot of gold jewelry is what we call 14 karat gold. And the 14 karat gold is not pure gold. If 24 is pure and you have 14, there's 10 carats of something else in there. But we can do this easy math and we can see what is 14 divided by 24. Somebody do that for me. I'm seeing stuff in the chat. 58. Well, 0.583 something. And when you convert 0.58 to percents, it's 58% gold. The rest of it, like if it's kind of a silvery color or a white color, they call it white gold. They've added silver for some of those other 10 carats or some other metal that makes it silvery. If they add like some copper to it, it makes kind of a reddish color that people call rose gold. And these are examples of an alloy. An alloy is mixing metals together. And when we alloy things, it would be like taking our metal atoms up here and saying like, well, that's actually, this is all gold, but now I'm sticking some copper in there so that it's not gold and not gold and not gold. Yeah. And so now I just have rose gold because I mixed some other metals in. And alloys, the science of alloys is called metallurgy. Let me type that out here because it's fun to say. You guys can all try saying it at home. I might have spelled that wrong. But metallurgy, go ahead and say it. You don't have to have your volume on. I just want to see you guys mouth the word. See, doesn't that kind of feels fun? You're smiling a little bit. Metallurgy. But it's the branch of chemistry that deals with metal alloys, which is mixing metals. And it's so basic sounding now, but back in the day, this was where we first got the science of chemistry working. And like being able to do stuff with metals is a game changer. If you were like ancient Rome Like steel was awesome back in the day. Second type of bonding. This one might be more familiar. Covalent. Co, that prefix, is usually like together or something. And valent is those outside electrons. So covalent, the word really means shared electrons that we have. And I tried to write, and PowerPoint does this cute thing where it gives me these images magically. But when I wrote non-metals out, it gave me the nuclear symbol, which was weird. But covalent bonds tend to be a non-metal bonding with another non-metal. So non-metal plus non-metal. And kind of the branch of chemistry that deals with a lot of covalent bonds is carbon-based chemistry, which we call organic chemistry. Yeah, in science, all organic means is made with carbon. So the organic stuff you get at the store, that's like an entirely different meaning of the word organic from the one we use in class. And organic chemistry is like all of the biological stuff is definitely organic, but also if you go to school, you kind of like this subject and you learn a lot about it, you can go make drugs, not the illegal kind, but like, you know, how we're trying to make a vaccine right now for coronavirus, that's organic chemistry. If you work for the people trying to cure cancer, making those kind of drugs, also organic chemistry. So it's some good stuff. And that's all covalent bonds. And those shared electrons aren't always shared evenly. There are some atoms that have a tendency to jack the electrons of other atoms. Oxygen is famous for doing this. Oxygen just wants to take your electrons. She's kind of a jerk that way. And our covalent molecules, and we say covalent molecule, our molecules tend to have lower melting or boiling points than metallic or ionic compounds do. And that sounds weird at first, but like my coffee, what little is left, is made of covalent bonds mostly. It's liquid right now, so it's already melted. You and me and everybody you know is mostly covalent bonds, and your skin keeps all that liquid stuff from just falling out. It's a good thing. So a lot of those things are liquid at room temperature or even gases at room temperature. All of the air that we breathe is a bunch of covalent bonds. Oxygen in the air, carbon dioxide, nitrogen, those are all made of covalently bonded elements. Actually, now that I'm thinking about it, most of the gases I can think of are all covalent bonds. I'll think about it some more and try to find some that violate that rule for you. But you can even think of like, we can all name one metal that's liquid at room temperature, right? Somebody just say it out loud. No, you don't know? The stuff that's in thermometers?
Mercury.
There we are, yeah, mercury. Mercury is a metal, but at room temperature it's liquid. It's the only one that's liquid at room temperature. There's another metal called gallium that if you held it in your hand, you would be warm enough to melt it, holding it there, but it's solid if you left it on the table. Maybe not Tucson room temperature, but you know, Paris room temperature, it's kind of colder. Now, I did mention that we're largely liquids, but our covalent compounds don't dissolve in water. So if you jump in the swimming pool, you will be fine. Where the next one on the list does dissolve in water, and those are ionic compounds. And we say compound with ionics, and we say molecule with covalent. Now, you will read a lot of times that one atom will take the electrons of the other atom, and it's not necessarily taken. It could be. So this is, one of those parts of debate, because our things and what we'll learn about is that there's kind of this balancing act between the octet rule, and that's how our elements want to have 8 valence electrons, and they also want to be electrically neutral. So they want to have the same number of protons as they do electrons. And this makes it like a weird balancing act, because if you are a noble gas, you're balanced and you have 8 protons and electrons, and everything else, has to pick. It's like on a seesaw. So sometimes an element will give up its extra electron to get 8, because that's pretty easy to do. Not all the time. Sometimes it goes the other way, but they can work this balancing act together. And if you get some ions, this is going to look kind of like my silly example with gold, but sodium chloride is my favorite ionic compound. It's my favorite rock. It's salt, but you'll get a bunch of sodiums, and then you'll have a bunch of chlorines sitting in between them, and they'll make like a row, and then you'll start a new row, and you'll get a bunch of chlorines next to the sodiums, and they just like sitting next to each other because one is positive and the other is negative, and if they sit next to each other, they get to be electrically balanced, and they have their octet rule figured out. We call what they have a formula unit, because this would be sodium chlorine, sodium chlorine, sodium chlorine, sodium chlorine. The individual piece of it is just one sodium chloride. But in real life, like, you've never held a salt, like you've held salt. It's always plural. Isn't that weird? Like the noun salt is plural. There's no S on it. But what is an individual salt? I mean, you could say it's that one grain. If we're in the classroom, I would take a teeny tiny hammer and hit it into 1,000 even smaller grains. They all look like cubes. It's actually pretty cool. But an individual 2 atoms would be the formula unit. They have higher melting points, generally speaking. So salt is a great example. If you put salt in the oven, it doesn't melt. You can melt sugar. If you melt sugar, you make caramel. But melting salt just doesn't happen at normal temperatures. And if you dissolve ionic compounds in water, they make something called an electrolyte. It is what plants crave. Yeah, that movie's older than you guys are, never mind. But this is what Gatorade is famous for. Gatorade is a bunch of different salts, different ionic compounds that are dissolved in water. And we have just enough time to talk about, where is Gatorade from? Anybody a college sports fan? Which team is the Gators?
Florida.
Yep, University of Florida. If you imagine you're playing football outside in Central Florida, it's very hot, but it's also humid, so you will sweat. And you won't cool down, so your body will make more sweat, desperately trying to cool off, and it just won't work. Now, you're losing water, obviously, but have you ever like accidentally gotten some sweat in your mouth when you're outside doing something and it tastes kind of salty? Yeah. So the athletes at the University of Florida were sweating their salts out, which made them the electrolytes left their body. And you need these electrolytes to transmit electricity in your nervous system. So if you're playing football in Florida's stadium called the Swamp, you'll perform worse. You'll sweat out all of the stuff that makes your nervous system work. So while you're sweating out all your nervous system stuff, you're just playing worse and worse. And they actually invented Gatorade to help out their football team. And they would win games and the opposing team wouldn't do so well because as you kept playing, it's like brain damage, temporary. It just made you not as fast on the throwing and all the football stuff. I have never worked out hard enough in my life to actually need Gatorade to replenish my electrolytes. Not that I'm a slouch. I've run a half marathon, but like they really sell you the idea of improving your performance and you got to be like way more on it to need Gatorade. And, you know, I'm just normal level of working out, not crazy time. But that's what I have for the class today. You guys are free to go. If you have any questions, you can hang out afterward. And yeah, I see green apple is your, there's green apple Gatorade. There's something wrong with that. But you guys have a great weekend.